All right, so this is part A. I went ahead and threw these in the calculator. 90 divided by 4.9 gives me 18.37. When I take the square root of that, I find that time is equal to 4.29 seconds. So I went ahead and put that in here. So part B asks how far from the base of the cliff does the stone strike the ground? So if I want to solve for the distance from the base of the cliff, what I'm looking for is this right here. And I'm going to call that delta x, okay? The reason it's delta x, not delta y, is because it's in the x direction. And the only thing it's going to have in common with the motion occurring in the y direction is that at the point when it hits the ground, that's when it stops moving in the x direction. So I'm going to use the same time. I know that Vx is equal to 15 meters per second because that's what I used at the beginning of the problem. I found that my time is equal to 4.29 seconds. And what the question is asking is, what is delta x? All right. The only equation that I can use in the x direction is going to be Vx equals delta x divided by t. All right. So I'm going to go ahead and solve that for delta x. If I multiply both sides by t, that means delta x equals v sub x times t. V sub x is given to us in meters per second. If I multiply meters over seconds by seconds, my seconds cancels out and I'm left with meters. So that should give me the right answer. So I'm going to say delta x equals 15 meters per second times 4.29 seconds. So I'm going to go ahead and say delta x equals, I'm just going to say 15 times, select it, enter, and that gives me 64.29. And that's 64.29 meters. So that wraps up part B. I'm going to go ahead and jump into C now. C asks, what is the velocity? And that includes the magnitude and the direction of the stone when it strikes the ground. So I'm going to label this A, that one B. All right, and if we want to know C, what the magnitude and direction of the stone when it strikes the ground is, if we draw a little triangle here, we have, slide this up a little bit, that represents our velocity in the x direction during the entire time because it's not going to change when we look here. It's got the same velocity in this direction the entire time. So that's going to be 15 meters per second from the start to the finish. Now my y velocity at the very beginning, right here, I've got no y velocity, so it would be 0 here. But after it's fallen 90 meters, it has some velocity in the negative y direction. So I'm going to go ahead and draw an arrow downwards so I know that it is acting downwards. I'm going to turn this so I can actually draw this straight. That is going to be our resultant vector. I'm going to go ahead and call that v, okay, because that is our overall velocity. We also want to find vf in the y direction to find that. And I'm going to relate my angle to the horizontal, so I'm going to call that theta right in here. So I'm finding the angle from here to here. It should be negative. If I don't want to make it negative, I can always wrap it all the way around, but I don't really want to do that. So to find VF in the y direction, we're not going to use any of the information we used for part B. We're going to jump back up here and look at things that are happening for part A. What we do know is that, and I'm going to go ahead and rewrite this underneath here. So I've got delta y equals negative 90 meters. This is landing underneath where it starts. Okay, time I found in part A is 4.29 seconds, and I haven't cleared my calculator, so it's still hanging out in there. I also know that acceleration is negative 9.8 meters per second squared, and my initial velocity is 0 meters per second. And I'm looking for my final velocity. I can use any equation that has v sub f in it. The easiest one to me to use, especially since we have a pretty exact answer in the calculator stored that we can just go up and drag down, is going to be vf equals vi plus acceleration times time. All right, I don't even have to solve it for vf. It's already in terms of velocity final. So I'm going to say velocity final equals my initial velocity is 0, well, that's pretty easy, right? Is equal to negative 9.8 meters per second squared. Go ahead and put that in parentheses. Times time, we got 4.29 seconds. All right, and that's going to cancel out one of those. So I know my final velocity ends up being negative 9.8 times, let me go ahead and grab my 4.29 here, and that gives me negative 42 meters per second, and that came out exact. All right. Now that is not the velocity that I'm looking for overall. That is simply my y component of my overall velocity. What I have to do is go ahead and look at my triangle right here again, and I'm going to say that equals 42 meters per second. Keep in mind this one is negative here, and this one is technically negative, but it's pointing down, and I have an arrow associated with that showing the direction. So I'm going to leave off the, it's negative 42. Okay, I'm just going to say 42 pointing down, and I'm going to call it a day. Okay. So if I want to find v, we're going to use the Pythagorean theorem, and we're going to say that v equals 15 meters per second, close parentheses, squared. I'm actually going to say v squared equals that, plus 42 meters per second, and that entire 42 meters per second is squared right there. All right, so I just read that line there. We go ahead and say v equals the square root of that, and just go ahead and put it on the calculator all at once because there's a bunch of extra steps. So if I do second square root of 15 squared plus 42 squared, that's going to give me 44.5, let's call it 60, right? So v equals 44.60 meters per second. All right, that is the velocity, that's the magnitude of the velocity that we're looking for. All right, and it makes sense because when we look at that, we have 42 here, 15 here, so it's going to be above that. So now I can go ahead and find my angle on the interior there. All right, to find this angle, we're going to have to use some trigonometry. I know that the tangent of that angle is equal to the opposite, right, 42. I'm going to say opposite over adjacent. Okay, so if I'm looking at the opposite over adjacent, I'm going to say tangent theta equals 42 over 15. In order to solve for tangent, I have to use the inverse of the function. So I'm going to say theta equals tan negative 1 of 42 over 15. And that's as far as you need to take it as far as writing stuff down there goes. You're going to need to plug it into the calculator by hitting second right here and then tangent right here. So it should say tan negative 1 above that. So go ahead and hit that and put 42 divided by 15. Enter, and it gives me 70.38. I should have done this before, but I am in degree mode, so I'm good. So my answer 70.35 is what I'm looking for. So that equals 70.35 degrees. All right. So that is how you solve question 1, parts A, B, and C. This is not the exact same information because I changed the numbers. But overall, what we're looking at is we're going to use the fact that my initial velocity in the y direction is 0. Go ahead and find the time it takes for it to drop, if just dropped. I'm going to find out how far it moves in the x direction over that time. And I plug that in here to find out my velocity or to find out my displacement in the x direction. I'm also going to use that information, not this part, but my initial velocity here to find the angle that it strikes the ground at. So all that really means is that when it does hit the ground, that it's hitting the ground at this angle to the horizontal, okay? And it's moving to the right at 15 meters per second, down at 42 meters per second, overall 44.60 meters per second, all right?